Okay, so we've got a diagram. It's always good to draw a full diagram of the system. This time, the line currents IR, IY and IB are the same as the phase currents, but we've got three line voltages and three separate phase voltages. So it's the phase voltages that are different in star, where that's the phase currents that were different to the line currents in a delta system. Yeah. Okay, so first of all, I, load current. What's the first thing we can say in general? As a balanced system, so yeah, I1 equals I2 equals I3. Because that's a balanced system. Yep. So what method are we going to go through to find, for instance, I1?
I've done 330.
330. Where?
330. I've done 300 over square root.
Yep.
Then over 1550.
300 over root 3. That little bit gives us what? Okay, so hang on. Always good idea to say that that's E line over root 3. Let's say it's E phase over, which is E1 on our diagram, E1 over R1, yeah, and E1 is equal to E line over root 3, isn't it? So you're then showing where that come from, okay, over R1. That's the 300 over root 3 divided by 1950, okay? And I'll just say that's the best practice, to always put that in and not, but if you calculate that and round it to three significant figures in the exam, you're not going to lose any marks. That'll be close enough. Okay? Yeah, okay. So with the value of 300, what does that come out as?
173. Oh no, sorry, that's the phase voltage.
Phase voltage is 173 volts. Yeah, I'll agree with that.
And then that's 88.8 milliamps.
88.8 milliamps. Yeah. So that's that part. How does that compare with the phase current in delta? Just flick them back. Each load current is 150 milliamps in delta with the same loads. Yeah? So, part B, we'll separate it again, just for the benefit of being able to compare with the faulted system. Okay, so for each load, P load is equal to what?
Square root 3.
Oh, you're doing the volts times current route. You could do that.
So I squared
Yeah.
3 times.
Don't really make any difference which way you do it. Okay. So I squared R. That's what's wrong with this?
Need to do 3 times.
Need to do
Yeah.
B3. I'm keeping it separate because we want to look at the change when we look at the faulted systems or the out of balance system. Do a comparison. Yeah. So I can put this times 10 to the minus 3. Okay. So I can do this. Well, you have to be careful there with your calculator. You must do that.
Is it worth it?
Yeah. Personally, I would just quickly convert that to amps. 0.0888 amps. That's what I would do. Because I've seen so many mistakes with the calculator on that, where they haven't, are just squared, and all you end up doing is squaring a times 10 to the minus 3. That's what your calculator will do. It's not what you wanted. That's what that will do. So you end up with inputting 88.8 times 10 to the minus 6, effectively. And that's not what you were looking for. Alright, so just be careful there. Personal preference is to do it this way. You should be able to quickly convert that 88.8 milliamps into 0.0888 squared times the 1950, which is 15.366, that must be 15.4 to 3 significant figures, yeah? 15.4 watts, therefore total power PT is equal to 3 times 15.4 equals 46.2. Okay, what does that? How does that compare with the total wattage in delta? Yeah. What was it in delta? 132. Okay. Okay, so all happy with that. They're the two basic systems which were essentially already covered anyway. How do we deal with this current thing? C. Looking at the diagram, how can we write an expression for IN? We're focusing on that node there, aren't we? We've got IN flowing out. We've got 3 currents. So we'll talk about 4 currents there. Yeah, if I make that circle big enough so we can see my current symbols, we've got IR, IY and IB all flowing into the node and the neutral current flowing out. So using my method of all the currents flowing in on one side of the equation, what's the law we're going to use here? Kirchhoff's current law, yeah? So the neutral's the one we want to find. It's the only one leaving the node, so put that on the left hand side of the equation, and then all the others added up on the other side. The neutral is equal to all those currents added together. So we can immediately make a statement by Kirchhoff's current law, IN is equal to IR plus IY plus IB. Okay. Now, looking at that, what's the value of IR, IY and IB? 88.8 plus 88.8 plus 88.8. What does that add up to? Adds up to the wrong answer then, Luke, doesn't it? Because we, as you've already said, we all know they add up to nothing. So where have we gone wrong?
Well, the customer get some of the clients. Is that right? Some of them are leaving the notes.
At an instant in time they are. Yeah, so what have we got to do? How have we got to do this arithmetic so that we take that into account? What do we know extra about these three voltages here, here and here? We know that's 300, but what else do we know about them? 50 Hertz. What else do we know about them that I haven't specifically put in the question, but is their AC? Something else? Not specifically, but assumed because of the star and the delta connected system. All three-phase systems. What's the basis of a three-phase generator? They're 120 degrees out of phase with each other. Yep. So, if we assume, and I usually tend to say the red phase is at angle 0, okay? So if we say, for argument's sake, this one, the angle is 0 degrees, the yellow one, angle is 120 degrees, and the blue one, the angle is minus 120 degrees. And that's why, if you look at the phases here, each one has only got 1 arrow pointing towards it. That voltage is between red, and that's positive that end. The yellow phase has got an arrow there, and the blue phase has got an arrow. I never put voltage arrows with arrowheads on both ends. Always indicate the polarity. And this bit indicates that they're 120 degrees out of phase with each other. That's by definition. Yeah? Therefore, these three currents must be, these are resistive loads, so that voltage and that current must be in phase with each other. So that this is a 0 angle current, this is a 120 angle current, and this is a minus 120 angle current. Yep. Now, can you add them all up and determine that they add up to nothing? I'll leave that with you for a couple of 3 minutes. Right, so we know that's wrong. Big X next to that, because we know that's wrong. We know it shouldn't be 266 milliamps. It should be nothing. Yeah. So what have you done? Yeah, so we need to convert each of these to Cartesian. So if we do them one at a time, I1 is 88 milliamps, 0.8 milliamps, angle 0 degrees, and that equals, in Cartesian, yep, I2 there's 88.8 milliamps, angle 120 degrees. That in Cartesian is 44.4, 76.9J, and I3 minus 120 degrees comes out minus 44.4. And quite clearly, if we add all that up correctly in complex arithmetic, we add the two columns up separately, that side and that side, they quite clearly add up to 0 and 0J. Yep, which is what we would expect. And I have to say, when I do this addition of 3 or more Cartesian values, I quite like to put them one on top of the other like that rather than across the page. Just a personal preference. I think personally I'll make less mistakes doing it that way.